Okay, these two problems, problem 75 and 76, are paired, so I'll try to explain how the problem 75 can be solved, and we'll move to problem 76. So the problem 75 is about solid sphere of radius r that has a spherically symmetrical non-uniform volume charge density. So the charge is not uniformly distributed for this case. So it's kind of the volume charge density is given as rho r equals to a over r, where r is the radial distance from the center somewhere here. This is center, and the radius is r, so r is somewhere within that range 0 to r. Okay, and a is a constant such that the density has dimensions m over l cube. So for part A, we have to estimate the total charge in the sphere. So for this part, I think we are kind of familiar with the volume element already in the previous problems as well. So that's dV equals to 4 pi r square dr. Okay, so it's kind of surface area of the sphere, 4 pi r square, times another, the dimension of length will give you the volume. Okay, it's like area times some length, let's say length, so that will be volume. Okay, so the charge element dq equals to rho dB. Rho is volume charge density, and this volume charge density times volume gives you the value of charge element dq. So as the problem already tells you about, the charge density is non-uniform for this case. So to estimate the total charge q, we use the integral formula. It's simple, like the integration of dq will be q, that's easy, where dq is rho dV. Okay, rho dV, and rho is given as a over r. This is rho. Okay, and dV, we already calculated this value, 4 pi r squared dr. So this is a simple case for the problem. So I'd like to collect the constant terms out from the integral, because they have nothing to do with the change in r. Okay, so the r ranges from 0 to capital R, that's the radius of the sphere. So it's a kind of simple integral, and you can easily solve this, and you will get 2 pi a r square. So the total charge in a sphere is q equals to 2 pi a is a constant which has a dimension of density, and r square is the radius of this sphere. So this is the total charge in a sphere. So for part B, so question asks you to find out the magnitude of the electric field outside the sphere, that is for some distance r greater than r, for example like this. So you have to find the electric field E at somewhere at the distance which is, let's say, r distance from the origin. Okay, or that is obviously greater than the radius. So magnitude of E outside the sphere is this. Okay, so I found and I think you all are kind of familiar with this kind of this type of problem, the spherically symmetric distribution. So electric field E can be written as this. So it's like q over 4 pi epsilon naught r is square. That's again the simple, and this r is the direction vector, okay, the unit vector along the direction of E. So it's kind of radially perpendicularly outward for our case. So we already calculated the value for charge, total charge q, so we can use that for our case and everything will be same. So we use this value, okay, and this is same, and you can cancel the terms, and so this is in the vector form. So if you try to find a magnitude, so you can drop that unit vector, so it will be a r square to epsilon naught r square. So this is the magnitude of the electric field at distance r, which is greater than the radius of sphere. So this is all about part B. For part C, it's the problem that you have to find an expression for the magnitude of the electric field inside the sphere at position r less than r. So it's kind of the problem that let's say this is the radius, so you have to find out the electric field at somewhere distance r, which is obviously less than the radius. So for this case, we can use Gauss law by drawing this type of Gaussian surface. It will be a spherical Gaussian surface. So for that, the electric flux will be E dot dA, that will be equal to charge enclosed by that surface, the Gaussian surface, divided by permittivity of free space epsilon naught. So here the problem is we need to find this q in, and dA is 4 pi r square. That's again the surface area of that Gaussian surface. The radius is r, that's 4 pi r square. And from part A, it's just we can change slightly change this problem. That's q in equals to 4 pi a r dr, like this. Okay, you can use this formula. Just you need to replace q by q in and everything will be kind of similar, but the limit is from 0 to r, obviously, because the maximum limit for that inside the Gaussian surface that encloses this q in, the amount of charge will be just 0 to r. So r dash dr dash is within that Gaussian surface, and whenever you do the simple calculation, the integral, you'll get 2 pi a r square. So that's the value of q in, the charge enclosed inside the Gaussian surface. So now you can use this formula, okay, this formula. So E dot dA equals to q in over epsilon naught. That's E dot 4 pi r square equals to, this is q in, okay, this is epsilon naught. So the magnitude of electric field would be a over 2 epsilon naught, or you can even write in the direction form as well. So that will be the E vector equals to a over 2 epsilon naught. along the unit vector r, direction of electric field. So I'd like to include problem number 76 to this video recording, because it's very simple and you just have to sketch this problem. Okay, a solid sphere of radius r has a spherically symmetrical non-uniform volume charge density, that's same, and you have to just sketch a graph of magnitude of the electric field as a function of distance 0 to r. So you just have to keep your eyes on the distance, that is 0 to 3r, like this r, this is 0 r, just in, it's like just the distance of separation is just r. So this 2r, this is 3r, this is r. Okay, and so obviously we already estimated this value, so that's why along y-axis I just write I just want to plot electric field. That's the maximum for, like, oh, this is inside the, that's like this here, it's at distance r. Okay, its electric field is a over 2 epsilon naught for that case. Okay, so as the radius, this r, the distance from the origin increases, the electric field decreases like this. At distance r greater than the radius, the electric field is this much. So obviously as the distance increases, the E is decreasing. Okay, so it's inverse square law, so that's why it will decrease, but it will never go to 0. So that's you have to keep your eyes on. So that's it for problem number 76, and that's all for that's all for chapter 25. We will move to chapter 26.